In progress.
Okay, so for quiz questions, let's look number 5 here. And after 5, hit a 3. All right, so on question 3, what do we got here? This is a frequency and red light, yellow light, okay. And then red light, which of the following correctly describes the relationship between wavelength and energy? Now, we know that if it has a high frequency, it has high energy. If it has a high frequency, it's going to have a shorter wavelength. So this goes back to the slide that if you do Roy G. Biv, it goes this direction for frequency and it goes this direction for energy. And then less wavelength. Okay, 319. All right, group 1, all elements that are in group 1. So what we're talking about for group 1 on 19, group 1, hydrogen, lithium, sodium, potassium, rubidium, cesium. What charge do they take on as an ion? Everything here, +1, +1, +1, +1, +1. How do you get a +1 charge? So how do you get a +1 charge is what we're talking about for number 19. And let's see, 28. Okay. A pair of electrons in the same orbital. Well, let's do that. So if you have a pair of electrons in the same orbital, let's make it a 4p, and we'll do something like this. And let's actually make the configuration 4p4. So that would be the configuration for 4p4 if we filled it according to Hund's rule, right? 3 up, 1 in each orbital of the same spin before we pair them up. Well, let's write out these quantum numbers for review anyway. A pair of electrons in the same orbital, that's describing this, right? There is a pair of electrons in the same orbital. And those quantum numbers would be 4 for level 4, 0 for S, 1 for P. The next quantum number would be a 1. The third quantum number would be -1, right? And the last quantum number, if we did them both together, would be plus and minus 1/2. How many quantum numbers are the same? First 3, right? The first 3 are the same. 28, 31. Okay, ionization energy. Is the energy needed to remove an electron? We know that as we go down a group, ionization energy decreases, and as we go across, ionization energy increases. Metals have high ionization energies because they want to gain electrons. Is that true or false? That's absolute top of the line BS, right? These metals don't gain electrons. If they gain electrons, they would have a negative charge. All of these metals lose electrons, give up electrons. So A is just complete BS. Non-metals will have high ionization energies because they want to gain electrons. So if they want to gain electrons, it's going to take a lot to get rid of them. I kind of like that so far. Metals will have high ionization energy because they want to keep their electrons. Metals want to give up electrons. Non-metals will have low ionization energies because they want to give up electrons. They do not want to give up electrons. All these non-metals over here want to gain electrons. What is the goal of all of these? To get the same electron configuration as the noble gases in group 18, which is how many valence electrons? 8. These non-metals, that's why fluoride, -1, it gains 1 electron to be like neon. Chlorine gains 1 electron to be like argon. Sulfur would gain 2 electrons to be like argon. 31, 30, 33. Which of the following ions are the smallest? We did this exact. Isn't this the exact one we did on the learning guide? Or close to it? This is it, isn't it? This is the exact same question we did on the last time we were here. 33, 44. 44, hydroiodic acid. If it starts with hydro, ends in ic, it cannot have any oxygen. The word acid means you have H+1. Hydroiodic acid. This then would be the same as we want iodide. It's the same as hydrogen iodide. Would be the same thing. And iodide -1. Okay. Now that completes this. It's due then. Some of this review, like this question, like 38 we did in class. Please, please, please. I call it training your brain. You want to train your brain to be able to do this question in 30 seconds, right? You need to sit down and say, hey, first thing you got to do is get moles. Again, I look at the exams and I'm thinking, we always put moles in a box. We always try to figure out. And I see a bunch of test questions. There's no mole. There's just no moles at all, let alone there's a number off to the side. Please, this is the most efficient way to do it. But go over these for review. I posted what's on the final for topics. You can go out there, and the best thing you can do is find the same topics from the take-home quizzes. Now you can start reviewing those slowly, way back from the beginning, correct? So there's a topic summary for the final out there. I opened that up. Okay. We are going into our last chapters. And this is chapters 8 and 9. So chapters 8 and 9, it's all about the electron. Where is the electron? What does the electron cloud look like? And what type of bonds do these electrons make, or these atoms make? Okay. So 8.1. And you want to start poking around in all chapters 8 and 9 as soon as you get a chance. So 8.1's on chemical bond formation and Lewis electron dot structures. So with that, chemists generally think of bonds as falling into 3 categories: metallic, covalent, and ionic. Now, the metallic bond, I like to explain it this way. And I don't think I've explained this, getting my classes mixed up. I don't think so. Now, let's say that the electricity that's running through these lights here comes from a periodic nuclear power plant. Where is the periodic nuclear power plant? in Red Wing, Minnesota. Okay? Now, let me ask you a question. We get this light up here because of the electron, right? It's the flow of electrons. That's what electricity is. I take a water hose, Wisconsin, unwind it all the way to Red Wing, Minnesota. And the water hose is full of water. If the water hose is full of water, all right. If I turn the water hose on in Red Wing, Minnesota, am I going to get water out of the hose in Eau Claire? If I push water into the end of the hose in Red Wing, Minnesota, am I going to get water out in Eau Claire, Wisconsin? Absolutely. It's already full of water, correct? If I push water in that end, if the hose is already full of water, I'm going to push water out this end, correct? Electricity is the same way. They're pushing electrons in from the power plant. You push electrons in at the power plant, you get electrons to go through your light with the switch. Just like the water, those electrons started at the power plant days ago, not weeks ago. I had maybe, I don't know what the calculations, I mean, my calculator. Just like the water that you would get, depending upon how much you flip your water. That started in so days ago. So a metallic bond is basically, they call it a sea of electrons. So for a metallic bond, I'll just draw it right here a little bit. If we have copper, and that's the best thing to, oops. And that copper has what we call delocalized electrons. And if I made this actually a copper wire, if at my power plant, I add electrons, if I push electrons in, this electron does not care what copper it's around. That's why they just call it a sea of electrons. So this electron here that I just pushed in can go around this copper. Well, this electron doesn't care what copper it's around. It can go that one. I can push an electron here. That electron doesn't care which copper atom it's around. And you could see that we could get just like a flow of water, we can get a flow of electrons. And since that electron doesn't care what copper it's around, and these are called delocalized electrons, by the way. That's the term, delocalized electrons. It gives metals luster. And you can bend this, and the electrons can reorientate, and the copper stays together. It doesn't break like brittle compounds. So a metallic bond they describe as this sea of electrons, and the key is these electrons don't care what copper atom they're around. Okay, now I think what I'm going to do is I'm going to go straight to Lewis structures, because you see these dots and it's like, well, what is this? So I'm going to page way into the back of this. And if you have this as notably or good notes, we are going to this page right here. Directions for drawing Lewis structures. So this is way up in page 24. Page 24. Okay, it says, write the skeletal structure, the arrangement of atoms within the molecule. There is going to be a central atom. That central atom is usually the lone atom or the atom with the lowest electronegativity, usually written first. Now, where do you find electronegativity? On the back side of your periodic table here. So we looked at electronegativities before when we did this bond triangle, right? Where is the most electronegative elements? Top right, fluorine is the most electronegative, but you got your high electronegativities here and your low electronegativities in the lower left. Okay. Step 2, and this just says carbon, nitrogen, phosphorus are usually central atoms. I'm missing, I got a typo there. Hydrogen is always a terminal atom, which is on the outside of the central atom. O is usually a terminal atom. Count the total valence electrons. The group number for each element is equal to the valence electrons. Well, it's the ones place. Now, we did that last time. So let's talk valence electrons real quick. Everything in group 1, how many valence electrons? 1. Everything in group 2, how many valence electrons? 2. Everything in group 13, how many valence electrons? 3. Group 14, 4. Group 15, 5. Group 16, 6. Group 17, 7. And group 18 has 8. Okay? Except for helium here, only has 2. 1 has 2. Okay, so we're going to count our valence electrons. And we have to add electrons for negatively charged ions. An example of that would be like NO3 minus. Subtract electrons for positively charged ions. An example of that would be NH4 plus. Okay. We are just going to go into this. The octet rule tells us elements gain, lose, or share electrons to achieve a noble gas configuration of 8 valence electrons. We are always talking 8 electrons. Everybody's happy with 8 valence electrons typically. Okay. Here is where I have this. Okay. Here's our compound that we want to write the Lewis structure out for, and it's CH4. Total valence electrons. Hydrogen. How many valence electrons for hydrogen? Uno, yes? Because hydrogen's in group 1. How many hydrogen atoms do we have? We have 4. 1 valence electron. So we have 4 for the hydrogen. Carbon, how many valence electrons for carbon? Carbon's in group 14, so 4 valence electrons. My total valence electrons is 8. Okay. Now, my Lewis structure for that. Hydrogens are always terminal atoms. Oops, let me go back. I want to make sure. It says write a skeletal structure. We could do that and count valence electrons. If I did the skeletal structure, This doesn't mean it is correct, but that would be kind of a skeletal structure. Okay. So I want to do this in order to make sure. I should take this last page off, or this page off. All right. So we wrote a skeletal structure. Count the total valence electrons. We did that. We do not have to add electrons because we don't have a negative ion. We don't have to subtract electrons because we do not have a positive ion. Step 3, draw a bond between the central atom and each surrounding atom. Okay, let's do that. A bond is 2 electrons. So I'm going to come in here. I've got a hydrogen. I need a pair of electrons here, a pair of electrons here, a pair of electrons here, and here. Now, the question is everybody happy at this point? Hydrogen wants the same number of electrons as the noble gas helium. And how many valence electrons does helium have? 2, right? Carbon wants to have the same number of electrons as neon, or 8 valence electrons. So if we look at this, every hydrogen has 2 electrons, right? Between the carbon and the hydrogen. Every hydrogen is happy. How many electrons total for carbon? 8, right? 8 total. Carbon's happy. I have 8 electron dots, 8 electrons. I'm allowed 8. That's it. I'm done. Now, this concept of bonding domains and non-bonding domains matches the blue sheet. So, for bonding domains and non-bonding domains, we are talking the central atom. And 2, 0, 1, 1, we'll look at those on a video clip here in a little bit. Bonding domains. How many bonds does the central atom have? Let me put this up here. For bonding domains, on the central atom, single bond equals 1. A double bond equals 1. Triple bond equals 1. A bonding domain is just a bond. It doesn't matter if it's single, double, or triple. Non-bonding domains are non bonded pairs of electrons. So if we look at this, central atom carbon, how many bonds does it have? It's got 4 bonds, correct? There's 4 bonds. How many non-bonded pair of electrons? 0. Now, I will take you through this blue sheet, basically, as you do this. So if we look up 40, my shape is tetrahedral. My bond angle is 109.5. My hybridization is Sp3. We'll talk about that coming up. So my hybridization is Sp3. All I'm doing is taking it off the sheet. We're going to explain that coming up. My electron pair geometry. My electron pair geometry is total possible bonds. Total possible bonds. My electron pair geometry just represents my total possible bonds I can have. And in this case, my electron pair geometry, I have 4 pairs of electrons. I have 4 bonds. This is tetrahedral. Tetrahedral. My molecular geometry is tetrahedral. That's actually what it is. We'll see an example of that. And my angle is 109.5 degrees. Polar, non-polar, we're not going to get to that for a while, but we'll explain that. Okay. That's our first Lewis structure. Let's do another one. We'll do the next one. So the next one, we have CCl2F2. So we could do a skeletal structure. Now, you might be asking yourself at this point, well, do those CLs go across from each other, next to each other? And the answer to that is it makes no difference. Because I'll bring the model next time we meet and you'll see that this is a 2-dimensional representation of a 3-dimensional molecule. So when you do tetrahedral, we wrote down 109.5. That's 3-dimensional space. It's 109.5. On paper, it looks like these angles are 90, right? But they're not 90, 109.5 for those. All right, we need to do our total valence electrons. Carbon has 4, group 14. Cl, 2 times what? Cl is in group 17 right here, right? 17. So chlorine has 7 valence electrons. Fluorine. 2 fluorines times 7 again. So my total valence electrons here, 14, 14, and 4 is 32, right? 32. All right. Now, what am I going to do? Let's see what step I am on. All right. So I wrote a skeletal structure. Count the total valence electrons. I did that. Draw a bond between the central atom and each surrounding atom. A single bond is a pair of electrons. Okay, step 3. I'm going to come over here and I have carbon in the middle. And I'm going to put a chlorine up there. I'm going to put a chlorine here. I'm going to put a fluorine here. And a fluorine here, and I'm going to zoom in. Step 3. That was step 3, right? So the skeletal structure doesn't mean that much. So step 1 says draw a skeletal structure. Okay. Step 2, count the total valence electrons. Step 3, draw a bond between the central atom and the terminal atoms. The terminal is the outside atoms. That's what we did, correct? Steps 1 through 3. Step 4. Place lone pairs of electrons about each terminal atom to complete their octets. An octet is 4 electron pairs around an atom, 8 electrons. Hydrogen can only have 2 electrons, okay? So I'm going to come in here with a different color, it doesn't really matter. But now I'm going to complete the octets on my outer electrons, my terminal atoms. Which means I'm adding, well, that blue is not showing up at all. So step 4 was to complete the octets on the terminal atoms. You might, well, I only added 6 electrons, which is fine because it's sharing those 2 with carbon, right? So when I go like this chlorine has 8 electrons, yes? This chlorine has 8. This fluorine has 8. However, I do this, that fluorine has 8, and that top chlorine has 8, yes? And then the central atom carbon, when you first do this, you might be, well, and I can go like this. That's carbon's 8 electrons, correct? Carbon has 8. My outside ones, they're sharing the pair in the middle to make the bond, right? They're sharing the pair in the middle. Everybody's partying up a storm because everybody is joyously happy because they have 8 valence electrons. They can't get any happier than that. Okay. Now, how many bonding domains do I have? How many bonds does carbon have? 4, correct? Is there any pair that are not bonded? No. So my bonding domains is 4. My non-bonding domains is 0. What is my hybridization? It's Sp3. Now, we can just write that down for now. It's going to be a week before we probably explain it. What is my electron pair geometry for a 4-0? It's tetrahedral. So my electron pair geometry is tetrahedral. My molecular geometry is tetrahedral. You're going to see a different one on the next one. And 109.5 degrees. My electron pair geometry is how many possible bonds I can get. And once we have non-bonded pairs, then these will be different. When we have non-bonded pairs, these are going to be different, which is the very next example. Okay, and the next example. We have NF3. Skeletal structure. Total valence electrons, nitrogen. Nitrogen is in group, right here, group 15. So 5 valence electrons for my nitrogen. Fluorine. I have 3 of them. And there are in group 17. So 7. So my total valence electrons is 26, huh? 26. All right, so that's step 1, skeletal structure. Step 2, total valence electrons. Step 3. I'm going to put my nitrogen, my lone atom in the middle, nitrogen. I'm going to make a bond between my terminal atoms. So it's a fluorine. It's a fluorine. And it's a fluorine. That's step 3. Step 4. Make the terminal atoms happy so they can go to Water Street. How do you make them happy so they want to go to Water Street? You have to complete their octets. So step 4 is to complete the octets on the terminal atoms. Now, complete their octets, meaning each of those has 8 electrons around it, correct? It's sharing the 2 in the middle for the bond. Each has 8. Who's not going to Water Street yet? Nitrogen, right? Because nitrogen only has 6 electrons around it. Okay. But how many electrons have I put down so far? 3 times 8, 24, correct? How many electrons am I supposed to have? 26. Let's go to another step then. So far, we went through step 4. Place lone pairs of electrons about each terminal atom to complete their octets. I did that. Step 5, if there are more electrons left, there is, we need 2 more electrons. Again, this is 24 electrons, we need 26. If there are more electrons left, place them as lone pairs on the central atom. This will sometimes lead to an expanded octet around the central atom. What is an expanded octet? More than 8 electrons. Okay, so let's do that. All we got to do is put our last 2 electrons around the central atom. That red shows up. Now, nitrogen's going to Water Street. It has 8, right? Everybody's happy. Happy Friday, everything's good for the weekend. Now, how many bonding domains do I have? How many bonds on the central atom? 3, right? 1, 2, 3. How many non-bonding domains? Right there, 1, correct? This is a 3-1. What is my hybridization for 3-1? And here's a 3-1. My hybridization is Sp3. Now, how many possible bonds could I have? My electron pair geometry does total possible bonds. I could have a 4th bond there, correct? So my electron pair geometry is a 4-0. So my electron pair geometry is tetrahedral. What is my true molecular geometry? My true molecular geometry is a 3-1. And a 3-1 on here is trigonal pyramidal. Now, I will show you some shapes, and Al will show you some shapes. Trigonal pyramidal, 107.5 degrees. Okay, notice that this is way at the end on page 25, but as this chapter talks about, these 2 chapters talk about electrons and valence electrons and Lewis structures, the best thing to do is saddle up the horse right away. Don't get bucked off. So we did some right away. Okay. I will show you some audio visuals for this next time we meet, but we had to just dive in. Okay. This is the last take-home quiz. And it looks like you can do 1 through 3 on this take-home quiz. It would be nice to try. I think you could do 8. And you can probably poke around an owl a little bit And I will show you some. I have lots of drawings in the learning guide as well. All right. Have a great weekend. Stay out of trouble, which means stay away from Water Street, right?